Okay, so just as before, you may go ahead and take your own set of notes, or you may go ahead and use the notes that have been provided for you in Schoology. This set of notes is called Compound Basics, Names, and Formulas. Most of this information should be highly reviewed from Honors Chem or from your summer work. All right, so first of all, we just want to talk about compounds. What is a compound? Compounds happen when atoms combine. So again, any substance made out of atoms of different elements becomes a compound. Okay. When we talk about compounds and what we know about them, there are a few different laws, chemical laws, that come into play. The first one is called the law of definite proportions or constant composition, which says in a single chemical compound, the ratio of its component elements is a fixed whole number ratio. So for example, in water, it's always 2 hydrogens to 1 oxygen. In carbon monoxide, it's 1 carbon to 1 oxygen. Okay. The law of definite proportion concerns the ratio of elements in a single compound. Okay, so that's important to understand. So again, if I have 2 parts of hydrogen and 1 part of oxygen, I'm going to get 1 part water. If I get double that, 4 parts hydrogen, 2 parts oxygen, I still get 2 parts water, because again, the composition always remains the same. Okay. The second law that comes into play is something called the law of multiple proportions. Okay, law of proportions, multiple proportions says it applies when 2 or more elements have multiple ways of combining into different compounds. So again, unlike constant composition or definite proportions, this has to do with different compounds that are made out of the same elements. Okay, so for example, if we have a fixed amount of one element, for example, nitrogen, and you combine it with different amounts of oxygen, a different element, the different amounts of the variable element can be expressed as a ratio of whole numbers. So, for example, nitrogen monoxide. If I go ahead and I look at the mass of the nitrogen in that and the mass of the oxygen in it, I get a ratio of 14 to 16 or 1 to 1.143. Okay? If I look at nitrogen dioxide and I look at those masses, I get a ratio of 1 to 2.286, which again, this number is 1/2 of that number. Okay? So again, they can be expressed as whole number ratios of each other. The last law that comes into play with compounds is something called the law of conservation of mass. Okay, and this was done by Lavoisier. And so Lavoisier basically took, and with a whole bunch of different chemical reactions, took masses before the reaction and masses after the reaction. And what he finds out all the time is that mass is conserved. So we have, in a chemical reaction, matter is neither created nor destroyed. It is transformed into something else. And there is our conservation of mass. Mass is conserved. So those 3 laws, definite proportion, multiple proportions, and conservation of mass, are what were used primarily by scientists in the early 1800s to basically start working with different elements and figure out how to combine them into different compounds. So you can go left side on this. So here we go. It says compound A contains 1.33 grams of oxygen per gram of carbon, whereas compound B contains 2.66 grams of oxygen per gram of carbon. Which chemical law do these illustrate? There's your choices. Make a choice right now. Jot it down. Come back. All right, so big thing here for me to recognize is we're talking about 2 different compounds, and you'll note that the oxygen is in a 2-to-1 ratio per gram of carbon. Okay, so again, multiple compounds, whole number ratios. This is the law of multiple proportions. One more for you. Compound A contains 1.33 grams of oxygen per gram of carbon, whereas compound B contains 2.66 grams per oxygen of carbon. If compound A has an equal number of oxygen and carbon atoms, what can we conclude about the composition of compound B? Take a moment, think about it, and we'll choose. Okay, so again, these are carbon and oxygen, so it wouldn't matter what we did in terms of a size. So maybe C2O2, right? Equal numbers of carbon and oxygen atoms. Okay, so this is 1.33 grams to 1 gram of that. So what would we say about the second one? Okay, well, it's got twice as many grams of oxygen, so it must have twice as many oxygen atoms. giving us C2O4. All right, so atoms combine to form compounds. The way that we represent compounds is by using chemical formulas. As you know, in terms of reading a chemical formula like H2O2, this tells me what elements are involved. The numbers tell me how many atoms of each of those are in one element or one molecule or one formula unit of the compound. When we talk about molecular compounds, they are composed of molecules and always contain only nonmetals. One particular type or set of molecular compounds are diatomic molecules. Di, of course, meaning two, atomic referring to atoms. So again, these are our elements, 7 elements occurring naturally that contain 2 atoms. So if we find hydrogen in nature, it always comes as H2. Same thing with nitrogen. It always comes as N2. Fluorine comes as F2. Iodine as I2. Okay. Lots of ways to remember this. Mrs. Larson refers to them as the sneaky 7. I like to remember the thing of I bring clay for our new house is one way that I do that. Or I have no brave and clever friends. I have no brave or clever friends. Okay. Or I have no bright or clever friends. There we go. Right. When we talk about chemical formulas, 2 formulas that we're going to be aware of right now. One is the empirical formula, which gives the lowest whole number ratio of atoms in each element. Molecular formulas give us the exact number of atoms in each element of a compound. So perhaps you have C2H4. That is my molecular formula. What's my empirical formula? Well, go ahead and reduce these both. So the empirical formula would become CH2. Other types of formula, structural formulas, look like this. They show how the atoms are bonded to each other. And last type of formula you can have are actually perspective drawings, which show 3-dimensional depictions of how the atoms are arranged. Ionic compounds, such as sodium chloride, are generally formed between metals and nonmetals. And remember that the stair-step line on the periodic table in general separates our nonmetals from our metals. All right, so that brings us to writing formulas. Okay, so when we want to write formulas for compounds, it depends upon what type of compound it is. All right, so we're going to go ahead and we're going to just start with ionic things. And in an ionic compound, the way that we're going to write formulas is we're going to go ahead and write down the cation, write down the anion, and then we're going to balance the charges to make it electrically neutral. The easiest way to do this is just crisscross. The magnitude of the charge on the anion becomes the subscript for the cation. The magnitude of the charge on the cation becomes the subscript of the anion, and you end up with Mg3. If the subscripts, when you do that, are not in the lowest whole number, we go ahead and we make them the lowest whole number. So for example, if you had Sn plus 4 combining with O minus 2, swapping them would give us Sn2O4, but we want to go ahead and we want to reduce that, so we would get SnO2. All right, in terms of naming these, we go ahead and we name the cation first, then the anion. So the cation takes the name of its element, so Na plus is sodium. The anion is named by taking the root of the element name and ending "ide." Cl minus becomes chloride, so BaCl2 becomes barium chloride. So that's if it's binary, if it's made of just 2 elements. If we have binary ionic compounds that have polyvalent cations, okay, polyvalent cations are cations that can have more than one charge. So for example, like copper plus 1, copper plus 2. Same rules as regular binary, except for we use Roman numerals for those that have multiple charges. Okay, so iron chloride can be represented by both FeCl2 or FeCl3, depending upon which iron charge we're using. Okay, so we go ahead and we put in Roman numerals for our systematic forms there. Okay, the Latin names have fallen out of favor. We don't typically use those. The reason why I make you memorize those is because sometimes old bottles of chemicals are still labeled with things like ferric and ferrous. Okay, so Cus Cu, S is a -2 charge. Copper then must be +2. So this gives us copper 2 sulfide. What if our compound has a polyatomic ion? Okay, well, still cation first, followed by the anion. We've memorized the ions on our polyatomic sheet. So Li2SO4, Li is lithium, SO4 is sulfate, and we're done. Okay, what about covalent compounds? Okay, so again, covalent compounds are formed between two nonmetals. The first element in the formula is named first with its full name. The second element gets its ending changed to "ide," just like we've seen before. And then we put prefixes on them to denote the number of atoms present. However, we never use mono on the first element. We just leave it blank. Okay, so N2O, 2 nitrogens would be dinitrogen, 1 oxygen would be monoxide. If we did something like NO2, first one we would normally write mononitrogen, but we don't use mono on the first element. So this is nitrogen. Second one becomes dioxide. Okay. All right, other things to name and write formulas for. Acids and bases. Okay, if we have an acid or a base, an acid that does not contain oxygen in it, okay, what we do is we take the H+ cation at the beginning of it and we give that the name hydro. For right now, we're going to recognize that acids are things that have hydrogens at the beginning of them. Okay, so then we go ahead and we add ic at the end of the name of the anion. So HCl, so that's hydrogen chloride. So hydrogen at the beginning becomes hydro. Chloride becomes chloric. Okay, so essentially my ride has hydraulics. So if you would normally put "ide" at the end of the anion's name, you would go ahead and you put "ic" at the end. So if an element ends in, or an anion ends in "ide," we put a hydro at the beginning and "ic" at the end. So HCl becomes hydrochloric acid. What about oxyacids? So these are acids that have oxygens in them. Those are going to be based on the original name of the oxyanion. If the name of the polyatomic ends in 8, we change it to "ic" for the acid. Okay, so for example, HNO3 is the ion nitrate. Okay, so we take the 8 and we turn it to "ic." I ate something icky is how I remember that. Okay, if we have one less oxygen than that, so that would become nitrite, ites turn into OUSs. Sprite is delicious, so that becomes nitrous acid. Okay, if I have one more oxygen, we would put a per in front of the ic version, per nitric acid. If we have 2 less oxygens than the 8 version, then we put a hypo in front of the OUS, so it would become hyponitrous acid. And then the last thing that we need to have a basic understanding of how we name is basic organic compounds. And again, organic compounds are good for our purposes, are going to be composed entirely of carbons and hydrogens, sometimes an oxygen in there as well. Okay. So the simplest hydrocarbons are called alkanes. The first part of their name, meth, eth, prop, has to do with the number of carbons in the molecule. So meth means I've got 1 carbon. Eth means I've got 2 carbons. Prop means I've got 3 carbons. Where does the ane come from? The ane comes from the fact that there are only single bonds in each of these substances. If we've got double bonds, we call them alkenes. So here we go again. Eth is 2 carbons. They're double bonded, so this becomes ethene. 3 carbons with a double bond, propene. 4 carbons, bute for 4, ene for the double bond. The last in this series is hydrocarbons with triple bonds. Those are referred to as alkynes. So here we go again. Eth, 2 carbons. Ine, triple bond. Prop, 3 carbons. ine, a triple bond. Bute, 4 carbons, ine, a triple bond. Okay, and then the last type of organic compound that we want you to be aware of is organic compounds that have OH groups on the end. These are alcohol groups, or functional group of alcohol. All right. If we have something else on there, there's things like ketones, for example. They would have a different group sitting on here. The only one I need you to know, though, are the alcohols, and that's if I put an OH on the end. All we do is we put an OL on the end of the name. So once again, meth, single atom, or single carbon atom, ane, only single bonds, all, hydroxide group on it. Okay. Ethanol, eth, 2 carbons, an, single bonds, all, OH group. 1-propanol, okay. Prop, again, 3 carbons, an, all single bonds, all hydroxide group on it. Okay. Last one I want you to notice is here something called carboxylic acids. And we're going to recognize carboxylic acids because they're always going to have this COOH in it. When we see that, we should recognize immediately that that's a carbon double bonded to an oxygen, single bonded to an oxygen, single bonded to a hydrogen. Okay, things that have this on them are called carboxylic acids. We do them the same way, but we put an ic acid on them. So for example, here we have 3 carbons, so that's prop, all single bonds in the carbons, ane, COOH on one end, oic acid, propanoic acid.